Picture a highway full of cars, trucks, and buses. Now, take away the tailpipes choking the air with pollution and replace that output with nothing but pure water. There is no smoke. There are zero carbon emissions left behind to trap heat in the atmosphere. This exact process is happening right now, powered by a device called a hydrogen fuel cell. For over a century, building a vehicle meant finding ways to scrub, filter, and minimize the damage of burning fuel. Removing the pollution entirely changes the basic premise of transportation, from damage mitigation to a clean energy system. A hydrogen fuel cell is a chemical factory inside a metal box. It takes raw hydrogen gas and converts it directly into electricity. Traditional internal combustion engines rely on controlled explosions, igniting gas to push pistons. A fuel cell generates its power without any fire at all. Without the violence of combustion, the mechanics run almost silently. The process operates with high energy efficiency, and the exhaust pipe stays completely clean. The fuel cell replaces the heat and friction of mechanical combustion with a quiet, direct chemical reaction. This diagram shows the internal architecture of a fuel cell. We start on the left, feeding pressurized hydrogen into the intake chamber. Once inside, the gas hits an anode, forcing the hydrogen molecules to split into distinct protons and electrons. These particles take different paths. Electrons route upward through an external wire circuit. That movement is the electrical current driving the motor. Meanwhile, protons push directly through a semi-permeable membrane in the center of the cell. On the far side, the paths cross again at the cathode. Outside oxygen is pulled in, merging with returning electrons and protons. The reaction concludes, outputting three things: a steady stream of electricity, heat, and pure water. By stacking dozens or hundreds of these individual cells together, engineers scale this microscopic choreography into a block powerful enough to replace a massive diesel engine. The environmental math is straightforward. A vehicle running on this architecture produces zero harmful emissions. But logistics matter just as much as emissions. While heavy electric batteries can take hours to fully recharge, a high-pressure hydrogen tank can be refilled at a pump in just a few minutes. This chart directly compares the capabilities of hydrogen fuel cells against traditional lithium-ion batteries. Hydrogen systems offer extended driving ranges that frequently outlast battery equivalents, while requiring a fraction of the downtime to refuel. That combination of long range and rapid turnaround makes the technology highly versatile. It can power city buses, long-haul freight trucks, commercial shipping fleets, and even entire building grids. Standard lithium batteries are heavy, and taking hours off the road to recharge a commercial truck is expensive. Hydrogen solves the weight and time problem, offering a realistic way to decarbonize heavy transport networks. National governments are recognizing this math. Billions of dollars are currently flowing into hydrogen research and development across Europe, Asia, and North America. The results are already on the streets. Entire fleets of hydrogen-powered transit buses are actively running their daily routes in major cities right now. Major automotive companies are prototyping consumer vehicles, while heavy industries like steel manufacturing look to hydrogen gas to cut their carbon footprints. When global transport networks, automotive giants, and industrial manufacturers all align their capital on a single resource, hydrogen transitions from a laboratory curiosity to a pillar of international industrial strategy. Yet, moving a global economy onto a new fuel source involves intense friction. There are physical bottlenecks slowing down the rollout. This infographic displays the current economics of the sector, mapping the steep cost curve of producing zero-emission green hydrogen against standard fossil fuels. Extracting hydrogen cleanly without relying on natural gas remains energy-intensive, creating a high price premium. Even if a consumer can afford the fuel, finding it is another problem. Public refueling infrastructure is scarce, concentrated in only a handful of specific geographic regions. Moving the fuel to new stations requires navigating complex physics. Hydrogen is a highly volatile, light gas that must be intensely pressurized or supercooled just to be stored and transported safely. Material scientists and engineers are targeting these exact pain points. Research labs are discovering cheaper electrolysis methods, and companies are designing safer, lighter composite storage tanks. The science of splitting the molecule is settled. The ultimate success of the hydrogen economy is a challenge of driving down costs and building a complex global supply chain. As the world works to abandon fossil fuels, fuel cells offer a practical bridge. By combining high energy efficiency with zero emissions, they provide a sustainable path forward for our most demanding machines. While the economic and physical hurdles are significant, the ability to generate carbon-neutral power makes hydrogen a necessary focus for a post-oil world.